We are Team 2, Team Dino-Mite, team members Grace, Brian, Alan, and Arjun. So our team name Dino-Mite comes from our backstory. Guru knows that he needs help saving his children, so he invents a time machine. He goes back in time and adopts a plesiosaurus, which is a dinosaur, and he retrofits it with mechatronics arms and a bunch of other things and brings it back to present day, and he's going to use it to help him save his children.
First, we will cover the purpose of this project. The goal was to score the most points in the ME 2110 Despicable Me competition by completing the 6 following tasks. First, we needed to launch the system with activation from the track. Second, we needed to clear the missiles from the child. We had to do this without hitting the child at all. Next, we had to place our shrink ray in our zone and our anti-shrink ray in an opponent's zone without directly touching the centerpiece. We also had to place a moon in the middle of the top of the centerpiece without coming in contact. Finally, the robot must complete all of these tasks in the 40-second time limit, otherwise it will be disqualified. This includes making sure the robot has fully egressed, meaning that it is outside the starting zone and not in contact with the centerpiece. There were many design problems that teams need to work around to accomplish these tasks. There were only specific energy sources that we could use. We could only use 5 rubber bands, 5 mousetraps, and the MyRio mechatronics kit to provide motion to the system. Additionally, there was a size constraint of 1 foot by 2 foot by 1.5 feet. If our bot did not fit within these dimensions, it would not be allowed to run. Finally, there was a budget of $100 for the creation of the bot, so teams needed to choose wisely what they needed to succeed.
To fully understand the problem, we made a house of quality chart. Along the side, we listed our customer requirements, and along the top, we listed our engineering requirements. It's a bit difficult to see on this slide, but our most important engineering requirement that we had to fit within our constraints was the operation time. This was the most important because if we went even a half second over the operation time, we would be disqualified, so all of our points would be for nothing. So as you can see within our customer requirements of the house of quality, our most important things we were looking for was for the system to be autonomous, it needed to be consistent, and it needed to finish within the time limit. These were the most important because if it wasn't autonomous and it didn't finish within the time limit, we wouldn't be able to score any points at all. And if it wasn't consistent, then we'd be able to be eliminated very early on in the final competitions.
Here's the specification sheet that we made for our system. Some important specifications are the size of the machine, the allowed energy sources, the resistance to fatigue, and the operation time. These are important because they prevent us from being disqualified from the competition and allow our bot to run consistently as the competition goes on. Fatigue is a specification that has not been discussed yet. It is important for our robot to have minimal repairs throughout its trials. A sturdy bot allows for consistent performance, as repairs lead to new variables that could alter the results of the competition. Thus, we wanted to have less than 2 repairs for 20 trials. It's unreasonable to avoid repairs, but minimizing the need for them will help in the long run. Some other important specifications are the autonomous percentage and setup time. The robot cannot be touched by a human during the running of the competition round, so it must be able to work on its own after the activation of the track. Additionally, there's a limited amount of time for teams to set up their bots prior to the round, 225 seconds, so we wanted the bot to be less than that to make sure we have a robot easily ready for each round, allowing for adjustment of position if necessary.
Here's our function tree. You can see that we broke the overall function of scoring the most points in the competition down to the sub-functions: obtaining energy, launching the system, clearing the missiles, shrinking the moon, returning the moon to orbit, ending the operation. And then within each of these, we kind of broke it down in some different ways that we could accomplish each of these tasks.
Here's the final morphological chart, which lists the product of functions in the first column. In the following columns, they contain graphical representations of potential solutions and ideas for each subfunction. For example, for clearing the missiles from the start zone without touching the children, possible ideas were using a circular moving arm powered by motor, driving into the missiles with mousetrap on each side, or just simply using large sweeping arm powered by rubber bands. Also, for placing the shrink ray and anti-shrink ray in correct zones, possible solutions were releasing the arm with mousetrap and solenoid, or extending the pneumatic piston. By listing several solutions to each subfunctions, our team could easily visualize ideas and choose the best and most efficient way to complete each task.
From the morph chart, we chose a couple combinations as design alternatives. All of them have wheels driven by a motor, which allows for the robot to get the egress bonus. Design 1 consists of 2 arms, one for the shrink ray and one for the moon, which are powered by mousetraps and held in place by solenoids. These solenoids are activated when the adjustable switches in the front of the robot are clicked by the plastic beacons on the rotating centerpiece. To clear the missiles, a swinging arm below the robot is driven by a motor. Concept 2 has very similar mechanisms as 1, with the only difference being that its shrink ray is propelled by a pneumatic actuator instead. These first 2 designs weren't chosen because the moon arm in this configuration isn't long enough, and a mousetrap couldn't provide enough propulsion. Design 3 also follows Alternative 1's design, but has some alterations which give it extra potential. The moon arm is powered by a motor, which is raised to give the moon arm extra height and length, which will allow it to place the moon in a high-scoring zone. Because a motor is used for this, the missile clearing arm now uses a rubber band as propulsion. This design wasn't utilized because of its lack of an anti-shrink ray arm.
We compare the customer needs from the house of quality to our 4 design concepts to evaluate and choose which concept meets the most needs of the customer needs with highest points. To structure the evaluations, a matrix was formed to rank how well the various alternative designs satisfy the customer requirements. For example, the first concept received high points in its ability to egress from the starting zone and being aesthetic, but received lower points in its ability to clear missiles and place shrink rate due to its structure. When looking at the fourth concept, which is most similar to our final design, it received high points in not damaging the environment, being time efficient, and egressing from the starting zone using 4 wheels. By summing the total points, our team could decide to use fourth concept as our final design.
The chosen design has been refined over much testing to optimize the team's usage of energy constraints. Both motors were utilized in addition to 3 mousetraps and 1 rubber band. Pneumatics weren't used because of potential unreliability, which is also why as many physical switches as possible were used, as opposed to things like the IR sensor. Mousetraps provide propulsion for the shrink ray and anti-shrink ray arms, which are initially held in place by a solenoid. Once the corresponding switch in the switch box is clicked, each solenoid pulls in the plunger and releases the shrink ray arm. Since the anti-shrink ray arm is on the opposite side of the switch box, it activates with a 2-second delay to account for the centerpiece's rotation. The design uses a direct-driven motor and wheels to drive in, which allows for both the egress bonus and for each subsystem to get closer to the centerpiece. The moon arm is a very thin wood appendage with a custom 3D printed basket, which is brought up and down by a motor. Its movement is controlled by a timer and activates close to the end of a round, so the moon isn't knocked out by competing devices. Lastly, to clear the missiles, the robot has a mousetrap next to the right front wheel which activates upon driving into the arena, as well as a rubber band-powered swinging arm which is held in place by a pin. This pin is released when the moon arm places the moon.
To fabricate our machine, we decided to use the bandsaw and jigsaw very heavily along with the manual drill. We decided to use more hands-on approaches because this gave us products that we could sort of design and build off of very quickly, as opposed to designing or CADing something and then trying to 3D print it or laser cut it, which often took hours if not days. We sort of had a product in hand within minutes that we could test right away and build off of very quickly.
In the preliminary moon shrinking competition, the robot was very inconsistent. In the first 3 rounds, the shrink ray didn't activate at all because the switch box was slightly out of place. Additionally, the robot wasn't driving well, which led to inconsistent missile clearing. To amend this, we put more rubber bands around the driving wheel and changed the switch box height. It scored 339 points out of 636. Most of the issues from the previous competition were fixed for the moon orbit competition, with the addition of a moon arm. This time, the robot was very consistent with the only issue lying in the moon only being placed in Zone 3, and a slight nuisance with the left mousetrap not triggering. The robot scored 596 out of a possible 836 points, and for the qualifying competition, the moon placement and mousetrap location needed to be fixed.
The next competition that we had was the qualifying competition. In the first round, our bot did not place the moon or shrink ray as it rotated improperly. After this was fixed, we scored much higher in our next 2 runs and placed first in the class with a total score of 759, which was good for 9th overall among all sections. More importantly, we learned how our bot should be improved for the final competition. We needed to make sure the moon arm was more consistent and could place in the first or second zone. We needed to fix the position of our mousetraps to clear the side missiles. We needed to make sure our bot aggressed away from the dome in order to get the 4 times aggression points. And finally, we needed to have proper wire management to clean up our bot. After this competition, we decided to rebuild our bot completely for a cleaner design with all of the same functions. The final competition started out shakily. In the first round, our robot did not drive out far enough to place the shrink ray, missing out on a very large portion of points. This was due to us fixing our wheels right before the competition. We placed 3rd in the first round, but edited the code for the bot to drive longer. After that, we placed 1st or 2nd in each round, making it all the way to the final round. Our highest scored round was 336 points, with a consistent 271 for most of the other rounds. In the final round, our moon bounced off the dome, giving us a 3rd place finish overall. Our bot's ability to perform consistently more than others allowed it to go far in the competition, even if the functions were not perfect. If we were to improve the bot from here, we would build a more consistent moon arm to maximize points. During the competition, it placed on top of the centerpiece most of the time, but just not where we wanted it to. We would also make sure that our bot drove reliably, so that it would maximize points when oriented correctly. Sometimes the bot veered to the right slightly, changing our missile clearing score. Finally, we would work on the aesthetics of our bot. While it was not our focus, it is important to have a presentable product that catches the eye, and something like paint would have made the bot more appealing.
Here is our final poster, which was created using Illustrator. By having a clear sequence of blocks with several topics from our goals and objectives to CAD images and takeaways, we could easily communicate with judges by showing the overall visualization of our final system. Especially, our team used infographics to easily visualize the method and takeaways by showing the icons and text together. When we look at the second column of the poster, it shows the main view of our system and 4 different subsystems from each view. Finally, we put the completion rate, which shows how our team scored related to our lab section and overall in 3 different competitions before the final competition.